Hello and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video we're going to go through section 6.5, the average value of a function. Hopefully you know from algebra and maybe some other places how to find the average value of a function, and that's simply by taking each value that you have, adding them all up together, and dividing by how many there are. Relatively simple. Same thing if we were trying to find the average value of a function. We would take multiple values of a function, divide by however many values we took, and that gives us the average value of it. Well, if I want to find a better average, then what I would do is consecutively take more and more points from that function so that I have a larger and larger value for n. That is starting to sound a lot like what we're used to for the integral. So what we can do is try to take this summation value that we've already created and make it look more like an integral. And to do so, what we need to do is try to introduce a delta x, where delta x is how long it takes until I get to another interval, or how wide each interval is individually. Well, if I know the interval is going to be set up as just how wide the interval is, so b minus a, divided by how many intervals I take, I can rearrange that formula. I can have delta x equals b minus a over n. I can divide b minus a to the other side and have delta x over b minus a equals 1 over n. That will allow me to replace the 1 over n that I had next to that summation with delta x over b minus a. So therefore I get 1 over n replaced with delta x over b minus a. Move the delta x onto the inside of the summation, because if I multiply all the values together times delta x, it's the same thing as multiplying each value individually. And then this summation with delta x is the definition of an integral. So we get 1 over b minus a times the definition of the integral. And that is our answer for how to find the average value of a function. Just looking at that function or that formula, that's a pretty easy one to work with. That's just the standard integral we've been working with on the function. No tricks or trips, anything, anywhere. The only new part is really this 1 over b minus a, which is just 1 over what the boundaries are. Nice and easy to work with. So let's solve for that. Let's do a couple examples. We'll find the average value of the function defined by f of x equals x times sine of x squared on the interval 0 to root pi. So that's pretty nice to work with. We could set that up as f average as 1 over b minus a, where b is root pi minus 0, so that's just root pi, times the integral from 0 to root pi of x sine squared x. Or not sine squared x, sorry, that actually would be different. Sine of x squared dx. Note how easy it was to set that up. All that is necessary now is to try to knock it down. Well, x times sine of x is two functions multiplied, both using the function, so the function of x, so that's kind of hard to work with. And we can solve that using our one trick that we do have at the moment, which is u substitution. If I say u is the value on the inside, the x squared, that means du would be 2x dx, which is everything else, these two parts. So I could say du divided by 2 equals x dx, which is what I have right there. And thus I can replace all of this with 1 over root pi of sine of u times du over 2. I can also mess with the bounds, because I can plug in 0 and root pi. Say a u of 0 would be, well, 0 squared, which is 0. U of root pi would be root pi squared, which is just pi. So then my bounds are now 0 to pi. Now I don't need to put u back in, or put x back in to where u is. This lets me solve that. If I move 2 on the outside, I get 1 over 2 root pi. And then the integral of sine is negative cosine of u from 0 to pi. Solving for that, if I plug in pi first, I get negative cosine of pi. Cosine of pi is -1 times the negative itself gives me +1. Minus, if I plug in 0, 0 into cosine gives me 1 times the negative gives me a -1. So that's 1 minus -1, or 2. So that's 2 over 2 root pi, otherwise known as 1 over root pi. And that would be my answer. Note that the majority of the work there was just solving for the integral, doing some integral steps, using u substitution, etc. The part that was setting up the integral for the average function took almost no time at all. It's not really hard to work with a lot of these questions with the average value of a function. Let's do an example that's a little bit more applied, though. Let's say, let's erase this box so I can see it better. Suppose the temperature in Fahrenheit of a metal bar 2 feet long depends on the position x according to the function t of x, or temperature, equals 40 plus 20x times 2 minus x. What we want to do is find the average temperature of the metal bar, and is there a point on the metal bar where the temperature actually equals the average temperature? All right, well, let's first find the average value. Whoop, still in the highlighter. Okay, F average. All right, so we have 1 over b minus a. In this case, we have a bar that's 2 feet long, so that means it should go from 0 to 2. So that's 2 minus 0. Plus, our bounds are also 0 to 2. Then we just put in 40 plus 20x times 2 minus x, which I can actually factor out to make 40x minus 20x squared dx. No need for u substitution here. Just need to solve this as it is a standard polynomial. I get 40x plus 20x squared minus 20 x cubed from 0 to 2. We've had this show up a lot. If it's 0 and we just have a polynomial, don't even need to worry about it. Just need to plug in 2. So we get 80 plus 2 into x squared gives me 4 times 20 gives me another 80. Minus 2 into x cubed gives me 8 times 20 gives me 160 over 3. So that's 1 over 2. That's 160. And then if I multiply 16 times 3, that gives me 480 over 3 minus 160 over 3. So that gives me 320 over 3, or divided by 2, gives me 160 over 3 again, as my final answer. So I'll say 160 over 3 degrees Fahrenheit. Now the second part of the question asks, is there a point on the metal bar where the temperature actually equals the average temperature? Well, there should be, and we should be able to check that. If this is the average temperature, we should be able to plug that in, 160 over 3, into my temperature function, into where Tx is, and solve to see where along the point of the line that happens. We actually simplified that earlier as 40x minus 20x squared. We can solve for this. So we can show it. We can subtract 160 divided by 3 over, so we get 0 equals 40 times 3 is 120. So if I subtract 160, I get negative 40/3 plus 40x minus 20x squared. That's a quadratic, and we can solve for that. We have x equals negative b, so negative 40, plus or minus the square root. Only one of these should work, or maybe only one of them, of negative b, or sorry, we already did negative b squared, so 40 squared, minus 4 times a, which is actually negative 20, times c, which is negative 40 over 3, all over 2a, which is negative 20. All right, 2 times negative 20, that's negative 40. Divide by negative 40, that's a 1. Plus or minus square root. That is 40 squared is 4 times 4 is 16 plus 2 zeros, so 1600. This is 3 minuses, so that still is a minus. 4 times 20 is 80 times another 40 gives me 320, or 3,200 divided by 3. And that square root is going to be divided by a negative 40. So we get 1. In this case, we can check both of them. But yeah, if we just take out that minus and make this a minus plus, that's all it does. The inside, that's 1600. If I multiply that by 3, that gives me 4800 minus 3200 is another 1600. So I get square root of 1600 divided by 3 over 40. So 1 minus plus. We know the square root of 1600 is 40, so that's 40 on 40 will cancel out. So that actually just gives us 1 over root 3 is what it does. 1 over root 3, so if I do 1 minus 1 over root 3, we can approximate these now to get 2 different answers. 1 minus 1 divided by root 3 gives me 0.4226. And if I do 1 plus, I get 1.5774. So yes, it actually happens twice. Because the bar goes from 0 to 2. So it happens at 0.4226 position-wise, so I guess 0.4226 feet, and at 1.5774 feet. Now, we should already know that the answer was yes anyway, because even if you plug 1 and if you plug in 0, you should get a value where they cross. So if I took that original function and I plug in 0, what I would get is 40 degrees. If I plug in 1, I get 80 minus another 20, so I get 60 degrees. And 160 divided by 3 is 53 degrees. So, since I found a value where it's above 53 and below 53, that means because it is a continuous function, because the function itself that we worked with was a continuous function, it should hit that temperature at least once between those values. Because it was a minus x squared, we did expect it to happen twice because it was a parabola. So what that leads to, what example 2 shows, is what is known as the mean value theorem for integrals. The mean value theorem for integrals states that if f is continuous on a to b, or it could even be open interval, then there is a number c between a and b such that f of c equals 1 over b minus a of a to b f to t. This basically means that if you plug it, there is some value that if you were to plug in, you would hit the average value. That's what this integral is. So there is some value between that interval where you will hit that average value. Maybe it'll happen more than once like it did in the previous situation, but it should happen at least once. This should also look very familiar to the mean value theorem for derivatives, which looks like the average, which is for the average rate of change, which is f prime of c equals fb minus fa all over b minus a. This fb minus fa is basically what would happen when you do this integral. You would end up with capital F of b minus capital F of a, and you subtract both of those when you do that integral. And then you would divide that by b minus a. So it's very, very similar. Let's do an example of that, and that's where we'll cut it, because this is a pretty short section. For this last example, what we're going to do is we're going to find all values that satisfy the mean value theorem for integrals for f of x equals 1 over x plus 1 squared over negative 0.5, comma 2. Well, what we first need to find is what the average function is. And then we can find where it hits where it hits those values. So we have 1 over, we have 2 minus a negative 0.25, so that's 2 plus 0.5. Integral from negative 0.5 up to 2 of the function 1 over x plus 1 quantity squared dx. Now, if you're worried about this one, you can also use substitution. You could say u is x plus 1, and du is simply dx. That makes a very easy u sub. So that gives you 1 over 2.5, which is actually 2/5, equals 1 over u du. The bounds of integration we can then change and say u of negative 0.5 gives me positive 0.5, because that'd be negative 0.5 plus 1. And then u of 2 will give me 3. So 0.5 up to 3. So there's an extra equals there, so 1 over 2.5. Okay. So that gives us, this is u to the negative 1 power. Oops. Sorry, this is u to the 2 power, so that's u to the negative 2. So that would be 2/5 times negative 1 over u, or negative u to the negative 1, from 0.5 up to 3. We solve for that. We have 2/5 times negative 1/3 would be first, and then I subtract away what happens when I put in 1/2 here, which would give me a positive 2. That's what happens when you put in 1/2 into u. So that gives us negative 1/3 plus 2. That gives me 5/3, which cancels out with the 5. So that gives me an overall answer of 2/3. You solve those. So that is the average value of the function. Now, the mean value theorem for integrals says that they should meet at some point within the interval from a to b. So somewhere between negative 0.5 and 2, I should get a value of 2 over 3. So let's solve for that. We have 2/3 equals 1 over x plus 1 squared. Okay, well, let's cross multiply. Let's make this a little bit simpler. I could say 2x plus 1 squared equals 3. So that equals 2x squared plus 4x plus 2 equals 3. And then if I subtract 3 over, I get 2x squared plus 4x plus minus 3 will give me minus 1 equals 0. Now this one, I don't think that we can FOIL out very nicely, so we could just use the quadratic formula to solve this. X equals negative 4, so negative b, plus or minus b squared, which is 16, minus 4 times a times c, so that's actually plus 8, all over 2a. A is 2, so that's 4. So that gives us negative 4 divided by 4 is actually just negative 1, plus or minus 16 plus 8, that's 24, which, so that's square root of 24 over 4, so negative 1. 24 can be represented as 4 times 6, so you could take out a 2 and cross out with the 4 to make root 6 over 2 as the most simplified possible. Now, that we should be able to tell is between negative 0.5 and 2, not by the subtraction, but only by the addition. If I subtract it, I'd become even more negative, so we know we have to check negative 1 plus root 6 over 2. But I know root 6 is slightly more than 2 because it's more than root 4. It's less than 3, though. So that means this overall is a little bit bigger than 1. Negative 1 plus a number a little bit bigger than 1 should give me a number a little bit bigger than 0. And that is between negative 0.5 and 2, so it's in the range. But if you don't believe me, we can put that into a calculator and check. This approximates to negative 1 plus root 6 divided by 2 making sure the division's on the outside, you get approximately 0.2247. So that's about where it happens. And if you do happen to have a calculator, you should be able to check that. That's our proposed value where it equal 2/3, so let's plug that in. 1 over 0.2247 plus 1 squared. I get 1 divided by 1.2247 squared, and we get about approximately 0.6667, or about 2/3. All right, so those are a couple examples of using the average value for a function, which should be relatively simple, particularly compared to some of the stuff we've been doing in Chapter 6. If you have any questions, feel free to put those into the comments down below or ask your instructor directly. With that said, I hope you have a nice day.